Hi, thank you for coming. My name is Dmitry. I'm the CTO of Fluence Labs. And today I want to discuss programming for distributed systems or programming distributed systems with the new p2p RPC language called Aquamarine. And I want to start with discussing sequence diagrams and whether they match reality or not. So here we have probably the most simple sequence diagram for client-server communication. We have two agents. We have a client. We have a server. Client sends a server request with some data attached and gets the response from the server. I generated this diagram from this code on diagram codes. So it's pretty straightforward. On the left, we have a description of the flow. On the right, we have messages. Pretty simple. We can have a sequence of requests from client to server. For example, if we have two different function or procedure to call, and in this case, this diagram is just a concatenation of two diagrams. So we have a request and response like we had previously, but we also do a request prime with the response of the first request to get some data that we need. For example, we could fetch the user ID with the first request and then resolve it to the user object with the second request or something like that. In this case, we have an unnecessary round trip because actually these two arrows in the middle are not needed. But as we cannot tell the server that it needs to pass the results of the first request as arguments of the second one, we need to do two requests. It could be another kind of diagram, like if this sequence of requests is done to a single server, probably we can install some kind of a proxy to that server that knows that these two requests can be done locally, concatenated locally. But often we have different servers like microservices or APIs, and they are not connected this way. In this case, we need to make the first round trip to the first server and then the next round trip to the next server. These two arrows in the middle are not required essentially, but we have to do it just to coordinate this process of requests and responses. One of the solutions to avoid this round trip and to simplify the flow to the client is to make a gateway and put it on the front of the complex setup with the different servers. In this case, we have even more arrows, and yeah, for the client, it seems more or less simple. But first of all, we have even more arrows. Second, actually, what we want to have is we want to make a request to the first server and then pass its result to the second server. But here we have a specially designed and configured gateway in the middle that not only hides this complexity, but also it encodes it, and it's make it strongly coupled between the protocol that is behind the gateway and the protocol in the front of the gateway. So if we want to, for example, change the API of server prime, or if you want to, for some of the clients, add another server or something like this, we need to probably recompile many things and do proper versioning for this system as a whole. If we forget about the client and say that for client everything is just okay, request, response, and so on, actually backend tend to be more and more complicated. We use many REST APIs, we use microservices, and so on. For example, this round trip between the gateway and the server, which is not necessary, by the way, but actually it could incur more round trips inside. For example, this server could have a database, and it could make another network request to the database and back. Here we have so many problems. Like, we still have an unnecessary round trip. We have many unnecessary round trips because maybe we could have this reply going to server prime directly. Maybe we can avoid all these 3 arrows, 3 network hops, and get the response back on the gateway directly, or maybe it could even go to the client directly. But as every server, every agent in this setup usually just provides an API that can be called in REST-like style or RPC or something like this. That's all that we can do for coordination of this request. And another problem is that there is no single place to see this sequence actually, except this diagram. So when I want to design this process, I open some tool set for sequence diagrams, or I'm going to the whiteboard, and I can draw all these arrows that control flow goes right and left and right and left, and so on. But then when I switch to code, I don't follow arrows when I'm coding. Instead, I'm following the vertical lines. Like, I know that server, when it takes this request of this kind from this party, from the gateway, it should do the next request to some database and then send the response. So it's nice for decomposition because it's not clear why this server should know that server prime exists. So this is clear and reasonable. But from the implementation point of view and from the conceptual point of view, we have 2 mindsets at the same time. We draw one thing, but we develop another thing. And when it's already developed, to understand what changes do we need to have to change the behavior of the system as a whole, we need to reconstruct this kind of schema in mind or on paper and hope that it fits reality. So this makes distributed systems even more complicated. Even though we have distributed flow controls like controllers and gateways and such stuff, but usually we have different concepts mixed in the same implementation. We use the same setup, the same language to solve 2 tasks. First of all, servers need to have some notion of the flow control. There should be some description what to do next. When the request comes, server does some pure computations like extracting arguments, validation, and so on. But then maybe it applies to a local state like cache or something like that. But then probably it needs to go over the network or to go to another process, and it should be described in the program. So this is one aspect. Another aspect is that the server needs to make its job, to make computations, to change the state, to build indices, to explain the domain or the part of the domain, and so on. And usually we tend to code both concepts in the same language, in the same setup, and it's hard to distinguish two. And that leads to having many reasons to redeploy or recompile or update the server. If we change the flow, the distributed flow, the control flow, if we split one of the servers into two or something like that, or if we change the data format or protocol, or if we change the computation themselves and need to modify business logic, we have many reasons to update the server, and that doesn't sound good. So in reality, the protocol, the sequence of these operations, and how the whole result is achieved is scattered. Implementation is split into different technologies, different servers. There is no way to see the whole picture. We often misuse the language because the setups which are fine for computations are often not so fine for asynchronous distributed flow management and vice versa. And of course, we have many solutions to these problems, just many. And there are different possibilities to factor out, to extract the network protocol from services. But the way how this process is and this design is organized has unnecessary constraints on the server implementations. Why? Because, for example, if you assume that your backend will be built with, I don't know, managed queue, for example, if you have a Kafka, then probably you will have message types or topics. You will subscribe to topics, you will publish to topics, and do such stuff, so that it will be working and it will evolve together with like Kafka, for example, and it will be probably it will be hard to switch to or to introduce a different approach when it's need to be introduced. Well, of course, it's possible to introduce a different approach, but it will lead to a different setup and different set of connectors and even more complex diagrams and protocols that you need to bear in mind. So this is doable, but it's hard. And that's why we are doing Aquamarine, and that's why I want to introduce Aquamarine, the language for distributed systems. So what was the purpose? What are the language design goals? First of all, we wanted to detach the distributed flow management from computations. Well, computations are done so different ways, and we have so many wonderful pieces of software that does it. Like, why to add to this? I don't know. Probably there should be reasons, but we want to focus only on this distributed part, on orchestration, coordination, and such stuff. We want to express the whole flow, the whole coordination, the whole sequence diagram in this single picture, in a single program, ideally in a scriptable program, so that we can update it without touching the services themselves. And of course, we want to apply some security constraints to enable reasoning about security for the services. But at first, we want to follow arrows in a sequence diagram instead of following vertical lines in implementation the distributed protocol. Then we want to have it modern and lightweight, developer friendly, not like huge XMLs. It should be reusable and composable so that we can reuse pieces of topology, not just simple functions, request, response, and so on, but also this layer that is usually very custom to different setups. Usually it's very hard to extract the this composability part of the distributed setup and to give it to people. So we wanted to extract it from services and present in a clear way. And it needs to be reasonable so that you can see it, understand what it means, and what it does. Let's try to re-implement the sequential flow and redesign, re-engineer the language semantics and syntax. First, I want to have the sequence of places where computations are made to be visible and like straightforward. Here we have on client. There should be a block of code. We do something on client, we begin on client, then we do something on server, and then we get back to the client. Then it would be nice to have not only this flow, but also some notion of computations. And here we have just we just follow these lines and say that on client, we want to have these computations and assign it to this variable. Then on server, we want to use this variable and extract the new data. And then we get back to the client. So if we take a look on the source code, we see the topology part, the moving from peer-to-peer, from machine to machine on the left, and we have an explanation of computations on the right. Then it's very useful for developers to have strict types for data, for functions, for arrows, and for just everything, so that developer gets feedback from the program as early as possible. But in distributed systems, it's often very useful to have structural typing, what's called structural typing in languages like TypeScript, when you don't need to have exactly the same type of the function. You need it to, like, if you have an object, you need to have the same fields that you expect. So if you expect the subset of the fields of the input object, then this input object fits. That's just the concept of structural typing in TypeScript. When you do protobuf or JSON, if you don't have this ability to add fields for free and to skip fields for free, it's really hard to manage the whole schema, because you need to make it absolutely fit. So that's about typing. The next concept is abilities. The concept itself is taken, is inspired by Unison language. It's a distributed language, pretty nice. So if we have some kind of computations, and if we don't want to express these computations on in the distributed language, then we need to resolve somehow how these computations should be executed on this machine. The basic thing here is a service. We can have the notion of types of the service, and then we need to resolve this service on a peer and to say how to make this peer perform this kind of computations. Here we have a service ID, and when we resolve a service with its ID, we can run functions, execute functions, and delegate computations to the service implementation. The whole flow can be expressed as a function. So, for example, if we have a request response, it can be expressed like this, and it's really nice to be able to provide some callback and be sure that this function will be executed where it's registered. Like when we register this callback, we register it on a particular machine, and when it's called, it should travel back to this machine and execute it. So here we have a block of the code that will be executed on server, and then we get back to the client to call the callback with the result, which is data of type bool. Actually, for functions, it's much better to have the return type, not only callbacks, but a common return type. And this is the syntax for returning. So we can extract the data on some server and then send it back at the response. In this case, we also can use functions in this language, in Aquamarine, to build the more complex functions, like decompose big code blocks into many functions and replace calls to services which perform computations, and to functions. So we can abstract this topological part if we need to, and reuse it in different functions. And finally, we have much more for expressing control flow. So here we have an imagination example when we have a list of servers to call functions on. We have for loop. We can run computations in parallel. So we are sending messages to each of the servers. We do some job here. Then we can have if, else, try, catch, stuff, and finally return. Let's express the diagram that we were considering before in Aqua. It looks quite straightforward now, and we don't have any unnecessary round trips. So what we want to get to application gateway. We have some configuration of the application so that we can resolve all the servers and service IDs somehow. It can be hard-coded, it can be resolved with some network service and so on. Then we go to application server, which can be resolved to as type service, SRV here, and do request on this server. Then we get to database and do fetch. Then we get to server prime and get the result and return this result at the return of the whole function, which gets us to the initial period of the client. So actually, life is not so shiny, and I have skipped a lot of code here. This won't compile because we're not in the diagram. It's the program, the actual program, that needs to know all the types of these services, of this data structure. It needs to check that input types and output types fits and so on. So we also need to have a description of data formats and APIs above. But it also described in this Aqua language. Let's take a look on how it's implemented on the compiler side. Aquamarine compiler is written in Scala with Scala cats. It's in Scala 2 currently, and it does 4 big steps. First, it's parsing text, splits it into tokens, and builds an abstract syntax tree that corresponds to the text. It has a relation to the text. And during this step, we can check grammar. The next step is a semantic verification. When we take abstract syntax tree, we apply some rules to the syntax tree to understand whether it's meaningful or not, and verify these rules. After that, we need to get the model of the program, like the intermediate representation of it, and finally generate some output, some code that can be executed. Let's take a look on each of the steps. I copy-pasted some Scala code just to give like a short hint on what happens on this stage. So for parsing the text, I use a cas parse library that finally gets to the abstract syntax tree in the form of a co-free co-monad. Co-free co-monad is such a data structure that has some label ahead, and it has many children which are the same kind of a co-free co-monad. Why it's nice? It's nice because we can abstract the type of the functor that holds the data inside, and I'm using chain, and we can use Catamorphism to convert this abstract syntax tree to something else. So we can have this abstract syntax tree and do the folding operation with this notion of folder. I think it's really nice, and it's much better than do folding one more time myself. Then when we have this abstract syntax tree, we need to extract semantics. And it's done with a catamorphism from co-free co-monad into free monad. So we have several algebras of free monads, free algebras for peer ID, for notion when we do some computations, for variables, for types, and for resolving abilities. Interpreters for these free algebras are stack-based, and all this structure allows to express semantics of operators in this style. So we have expression separately, and we have semantics separately. And for each expression of the language, we describe the constraints, the semantics. So for example, for on expression that moves computations to a different node, to a different peer, we need to ensure that this peer can be converted to string. Then we move to this peer, we get it into the scope, and then we begin the scope for the ability resolution because for each peer we need to figure out how to resolve abilities on this particular peer. And at the end, we need to get the same things inversed. We need to clear the scope of abilities, erase peer ID, remove it from the stack, and convert it to the model. So the output of executing free monad with the semantics is either errors or the model of the program. And here we have the expression that does folding. It's pretty dense and like simple, just around 10 lines of code. So what we have here, we take the node of abstract syntax tree with all its children, and we evaluate it into a new free structure. And to do so, we do right folding for right biased operators. Then we do left folding for left biased operators. We have both right biased and left biased operators, but that's probably beyond the scope today. But in general, it looks pretty simple. As a result, we have the model of the program, and we need to compile it. But to generate the resulting code. Well, the question is what to generate. Okay, we have such a nice language. We have topology expressed on the left, computations on the right. We have this notion like we can remove round trips and so on. That's nice. But how to compile it and how to execute it? Should it be compiled to like WebAssembly or to Java or to native code or to what? And now it's time to speak about the Aquamarine runtime because it's a very specific distributed runtime that's also implemented. So to express distributed systems, we need to rely on some theory, and we took calculus, process calculus. It has a very constrained set of operations like input and output, sending message, receiving message, combinators, sequential, product or coproduct or product. So parallel or exclusive. It has a match and mismatch so that we can run computations in case some condition holds or not. There's restriction, replication. So finally, it's a very constrained, very narrow set of operations, but thanks to the theory, we can be sure that it's enough. And for Aquamarine, we made an Aquamarine intermediate representation, which is based on p-calculus, and we implemented an interpreter that can execute these kind of operations. Aquamarine intermediate representation looks like this. So it's like S expressions with many braces. It's pretty hard. It's pretty primitive and pretty hard to code in. But as it's a compilation target, no need to care too much about that. But it looks like this. We have sequential operations, we have parallel, we have calls and such stuff. To execute these distributed flows, even if they are expressed in this low-level theory-backed implementation, we need to send some data as well. So the whole scenario, which could be expressed in a single Aquamarine script, is coordinated with use of a single data object. And as we have a distributed stub, writes to this object may be done in parallel. So we have a fork behavior when we do some computations in parallel on different nodes. And we have join when we merge these flows back. That's why data objects must form a conflict-free replicated data type, so that developer can just code what they need and be sure that there will be no conflicts when complex scenarios are made. And finally, we need to delegate computations to the nodes. And this delegation is pluggable. Aquamarine interpreter can delegate goals to anything that conforms the contract of air, where we have a location of computations per ID and a pair of service ID. It could be service name or some notion of a part of functionality to route to it, and a function name to point on the distinct part, like piece of code entry point to execute. Then it takes 0 or more arguments and can yield a result. So anything can be used. For example, JavaScript callbacks, like functions that just take this pair and provide some output. But in Fluence, to form the Fluence network, the open network backed with Aquamarine technology, we use a Fluence compute engine, which is WebAssembly based, and it provides WebAssembly interface types for strict typing of data and computations. And it can run both pure modules, pure computations, or effectors like write to file system or proxy calls to REST services and so on. And for open networks, it's very important to have these computations sandboxed. And all of this is this sandboxing and module distribution and providing as a service deployment, provision, and so on, is provided with a Fluence compute engine as a default. So with Fluence, the network, it's possible to do not just distributed flows, but also peer-to-peer RPC calls. In general, exposing functions to the peer-to-peer network, exposing like any functions is not very secure, and providing raw microservices to the network is hard, because you need to consider security here. But it's bundled within Aquamarine, so arguments of all the functions and responses are signed with the public key, with the private key, which corresponds to public key, which corresponds to peer ID. Connection is encrypted with a libp2p and noise protocol, or libp2p. Origins of data, of inputs of all functions is tracked and verified. So there is no man-in-the-middle attack possible. So that's why services can be added to the network and composed into different applications. Here we have an image of what it could look like if we implement a distributed peer-to-peer chat service in Fluence. Actually, we have it implemented as an example. So we can express the whole flow, like we need to get from browser to relay that will make us connected to the whole network. We can resolve other peers in the network. We can express that we need to do many things in parallel and to have something sequentially. So the whole script, the whole sequential diagram that corresponds to this script can be expressed as a single Aquamarine function. And there could be many different applications in parallel which use the same services but for different purposes. So you can implement a chat that some other developer can extend, add functionality to it, and such stuff. This means that Aquamarine runs in browsers. So Air can be interpreted, executed in the web browser thanks to having an interpreter compiled into WebAssembly. And all the browsers are peers of the network. So if you can find a path to the browser, if you know what node, what addressable node the browser is connected to, then you can reach this browser or the Fluence network. And that's how that's what it looks like if you compile a simple Aquamarine script to TypeScript. Essentially, it's an Air script wrapped with types and functions, so that finally, for the front-end developer, it looks like just a function that takes several arguments and returns a promise. So it's very straightforward to use. As Aquamarine is the language for distributed stuffs, distributed applications and networks, then different distributed algorithms can be implemented in Aquamarine and should be implemented. So we can begin evolution of distributed algorithms detached from languages, from computational languages. So we can implement Kademlia, for example, that expects that Kademlia address book on the nodes provides some API, but that's all. So we can detach computations from topology, we can express topology in Aquamarine, and we can share, we can package topologies, simple ones and complex ones, as Aquamarine libraries and reuse them across projects. I think it's a huge achievement because previously these topologies were usually bundled with the particular solutions. Why to be implemented? Because they are not implemented yet. We are working on Kademlia, but yep, request response, of course, is implemented because it's straightforward. And all of this is being done by Fluence Labs, and it's available as a public permissionless Fluence network. So you can take a look on it. And just to sum up and recap, Aquamarine language simplifies distributed systems development. It's pretty clean and it's already there. So thank you for your attention. To learn more about Aquamarine, take a look on our GitHub, Fluence Labs organization. We have many repositories for computations, for the node, examples, and so on. And subscribe our Twitter, join our Telegram. I'll be happy to have any questions if there are any. That's all. Thanks.
Thanks.